15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello and welcome. Thank you for joining us on yet another edition of the podcast we affectionately call Space Nuts. My name is Andrew Dunkley, your host, and with me as always is Professor Fred Watson, Astronomer-at-Large, as against a large astronomer who obviously spends too much time behind the telescope eating Twinkies. Hello, Fred.
I'm not familiar with Twinkies, but I did have a Twix today. How's that?
That's close enough. Any
Yeah.
sugary treat you eat in bulk?
Well, I do. I
counts.
tend to, a bit addicted to sugar, really.
Aren't we all? Aren't we all? I've seen documentaries about it. It's very scary. But I can't stop myself.
No, you can't. Sorry.
Now, Fred, today we're going to talk about Voyager 2 because it's just crossed the threshold. It is now in interstellar space, or the interstellar medium, I suppose, to use the proper terminology. And we are also going to look at the what could be the lowest mass black hole yet discovered. This thing is small enough to get into a science fiction novel by Andrew Dunkley called Parallax. Actually, no, it is too big for that. But we will investigate that, and we've got a few questions. These ones all came in recently, and I've got a confession to make, and my wife's going to hate my guts for saying this, but the other day she was telling me how she cleaned out her Gmail account. I said, oh, mine's got 14,000 emails in it. What do you reckon? She said, give it here. And she went, click, click, click. I said, but I don't want to lose all my questions from Space Nuts. And she went, what? Guess what happened?
Oh, that's all right.
They
Good.
were all vanquished. All vanquished. I spent a couple of days Googling all the ways and means of getting everything back, and I actually succeeded, which was quite surprising. But not only did I succeed in getting those ones back, I got all the ones that we've already done over the last 3 years.
Okay. Never mind. That's all right.
Oh, dear. You've got to love technology until it breaks. Anyway, let's get on with the business of the day, and that is the remarkable journey of Voyager 2, notwithstanding the wonderful journey of Voyager 1, but it's got a broken bit. That's why Voyager 2 is a little bit more interesting in terms of its recent achievement. Where is it exactly? It's so many gazillion miles away, 119.7 astronomical units would be my guess, but what's the latest?
Yeah, that's right. It is 119.7 astronomical unit. An astronomical unit.
What a coincidence! That's what I thought.
Is the distance, the average distance between the Earth and the Sun, which is 150 million kilometers.
Wow.
Or as I used to say when I was a kid, is it 93 million miles? I think it's 90. It might be 92. Anyway, about 90-ish million miles.
Yeah.
But 150 million kilometers, since we all use kilometers in this country these days. But it's a staggering distance. It's actually not as far as Voyager 1, which is the most remote human-made object. Voyager 1's a little bit further along the track. But Voyager 2 is about 17 billion kilometers from the Sun. And why is it in the news? Because it has just crossed the helio sheath.
The helio sheath.
Yes, the helio sheath is...
Because I've heard of the heliopause, because I saw that in a doco once about Voyager 1's journey.
Yeah.
And now Voyager 2
what we're talking about, basically, is the boundary between the Sun's magnetic field and the interstellar magnetic field. And it's not just a simple boundary, it's complicated. So there is a heliopause, that's the transition, but there is also a helio sheath, which I think is the part on the sort of leading edge of the Sun's field of magnetic field of influence. Might be wrong there, but I think that's what it is.
Good enough for me, Fred.
Yeah, it sounds good, doesn't it? Actually, there's something else too, which I think is further in towards the Sun, and that's the termination shock. And I have to say, my knowledge of particularly magnetic physics in the interstellar medium, is not as detailed as it could be, and so these terms are ones that probably mean as much to me as they do to you, but basically they mean the edge. They're at the edge of the sun's magnetic influence. Now, just one thing to preface this discussion with is that they're not at the edge of the sun's gravitational influence, because gravity goes on forever. And there are objects which are bound to the sun which are much, much further out than either of the Voyagers are, and these are comets. There is a cloud of cometary debris which circulates around the sun. It's called the Oort cloud, and it's a lot further away from the sun than we're talking about now. But those comets exist whilst they're connected to the sun gravitationally, they are actually orbiting the sun, but in the interstellar medium. So they're not connected magnetically to the sun.
Wow. Yeah, I forgot about the Oort cloud. I mean, it's very hard to think in terms of the enormity of what we're discussing sometimes, that just the massive size of the things around us that you can see and look through and witness, but you just don't get it. And the only way to get it is to get out there and look back, and we haven't really had too many opportunities to do that.
You could also get it by reading, a science fiction novel by Andrew Dunkley called Parallax.
That would do it.
Or you could read a book called Cosmic Chronicles by Fred Watson, which
that's
also
rubbish. That is.
Oh, it's rubbish. So not only is it rubbish, it's going to have it's not rubbish at all. It's a very good book. It's going to have a different title in the rest of the English-speaking world, because the American publisher, Columbia University Press, thought that the original title here in Australia of Cosmic Chronicles wasn't exciting enough, so everywhere else in the world it'll be called Exploding Stars and Invisible Planets.
There's a really old one by another author called Cosmic Barnacles. It's really boring. It's very slow. Back to Voyager 2.
Yeah. How did we get onto that?
Oh, by the way, those books are available on the Space Nuts website via our shop.
I didn't even know that.
Funnily enough. Yeah. Voyager 2 is fascinating because it's been able to offer us some information now that it's crossed that threshold that we were talking about. And it did something that Voyager 1 couldn't, because it had a broken bit, as far as I understand. Yeah,
that's right. So the Voyager 2 has got all its faculties still operating. What it's done is measured the plasma density. That's the density of these ionized particles that have been denuded of their electrons. And the really interesting bit is that this plasma density, when you leave the sun's field of influence, it actually goes up. It jumps upwards hugely. And you might expect it to be the other way around, because the sun's a relatively nearby object. It's streaming out these, the particles, the solar wind, and you might think that the solar wind, having its source nearby, would be much denser than the interstellar wind, if I can put it that way, the plasma that's caused by interstellar space. But the reason why it's the other way around, and it actually is the other way around by a factor of 20 in this case, the measured values are actually a factor of 20 different. In fact, I can give you the numbers. I might just do that. And this is particle density in the our side of the heliopause. That's the as we said earlier, the boundary between the two. It's about 0.002 particles per cubic centimetre. So that means you've got much less than 1 particle per cc. But on the other side, it jumps up to almost 0.04 particles per cubic centimetre. And what that's telling you is that there are 20 times as many particles beyond the boundary as there are on this side of the boundary. And it comes about because their effective temperature of that that solar wind is much lower. Sorry, that interstellar wind is much lower. Its temperature is lower, and that increases the density of the particles. As temperature goes up, the density decreases. So that the temperature of the solar wind, if I can put it that way, is much higher than the temperature of the interstellar magnetic on the interstellar particle flux. So yes, interesting stuff. What's also interesting, I think, about this is that when Voyager 1 crossed this boundary in a completely different direction, because I think Voyager 1 went to the north of the equator and Voyager 2 to the south. I think I'm right in saying that. It might be the other way around, but they are different. So because the sun's magnetic field of influence, certainly in this direction, is roughly spherical, you'd expect these two distances from the sun when the spacecraft cross the boundary to be more or less the same, and indeed they are. Slightly different, but not very different. So we've just seen Voyager 2 cross. In fact, it's not just is the wrong word. It's actually about a year ago, but this is, the results that are being analysed.
Yeah.
We've seen it cross the heliopause at a distance as exactly as you said of 119.7 astronomical units. 6 years ago, Voyager 1 did the same trick in a different direction, and the distance there was 122.6 astronomical units. So they're really relatively small differences in the in where they cross in terms of the distance from the sun. I think that's quite remarkable. It tells you that this region around the sun, certainly at this point, is roughly spherical, and it's good to have the all the theoretical predictions actually basically demonstrated by these measurements.
I wonder what Gary Flandre would think of it all.
I don't know. Why don't you ask him?
Is he still around? Isn't he the guy that thought of the idea of sending the Voyagers out there because he realised the alignment was
the alignment
correct?
Of the planets? Yeah, I'm not sure about the identity of that person, but I trust you to have found that name from a reliable source and not just a science fiction novel called Parallax or something like that.
No, it's not in there.
No,
but I think it was him. There was also another fellow who headed up the project, Harris Schermeyer, and he has passed away. But he probably was around long enough to understand the ramifications of the missions, because they did what they were designed to do, but then they kept on going, and going.
And so that the Voyager project has been extended by NASA about 10 times, I think, because originally it was just a 4-year mission. And just to remind Space Nuts listeners, 1977, I think, was the year that the spacecraft were launched. Voyager 2 was launched before Voyager 1. And Voyager 1's mission involved flybys of Jupiter and Saturn, but Voyager 2 included those two and Uranus and Neptune as well. And it was exactly as you said, it was a few individuals who realized that if you were quick about it, you could get a spacecraft off into the wide blue yonder. Then you could take advantage of the alignment of these planets and use the ones that you're flying by as gravitational slingshots. So you push them on further out into the solar system.
Yeah, Gary Arnold Flandre was the one who made that discovery. And
very good. It
was sort of a backroom concept that became something super extraordinary.
Yeah.
And still is.
It is. They're sort of magical machines, really. Just to kind of tie up one other loose end, they both are powered by radioisotope thermoelectric generators, RTGs, which have a limited lifetime. As the power gradually falls away from the heat that these the boxes of plutonium are providing, the various instruments, non-critical instruments, will be switched off as time goes on, and at the end we will only have telecommunications, just telemetry going between the Earth and the spacecraft, but we don't expect that to happen until round about 2032. So there's still life in the old spacecraft yet, and we hope we'll hear more about them as they venture into space. At it's roughly, I think their speed is of the order of 17 kilometers per second or thereabouts, and they'll keep on going, probably forever.
Fantastic, yeah. They could probably recharge by doing a flyby of Chernobyl or something. That might work. All right, more to learn, I'm sure, from Voyagers 1 and 2. But yes, a milestone again reached by Voyager 2 recently, and the data coming back is so very intriguing. You're listening to Space Nuts with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, welcome back, and a big hello to all our followers on the Space Nuts podcast group on Facebook. Hey, I got it right. That doesn't mean I'll get it right again, but thank you for following us there. We get a few people joining the group every day, I notice, and it's a pleasure to have you all aboard, whether you listen or read or both. But a lot of the stuff we talk about ends up on the podcast group Facebook page. So if you're not a member of the Space Nuts podcast group, just look it up on your Facebook search engine and join us. We'd be happy to have you along. I occasionally partake in conversation. Fred's not a Facebook user, which is probably the safest way to be, Fred.
Yeah.
It's fun but addictive.
Yeah.
Now let's move on to our next topic, and that is the black hole, maybe, which could be the lowest mass black hole yet discovered at 3.3 times the mass of our sun, which isn't super massive at all, really, when you think about it.
It's not. That's quite correct. So this is a very interesting. It's a very interesting set of observations that have basically arrived at this conclusion that what we found, or what astronomers have found, is the smallest yet known black hole. But it might be the biggest yet known neutron star.
Here we go.
Yeah,
potato.
Well, it's always, there's always caveats in these things. So let's just review what we know about black holes. They come in basically 2 classes. The supermassive black holes, which are things with masses millions or billion times the mass of the sun, which sit at the centers of galaxies, and they've probably grown that size by gobbling up lots and lots of debris and material that have surrounded them over the maybe 12 or 13 billion years that they've been in existence. But then there's what we call stellar mass black holes. These are black holes with masses which are greater than the mass of the sun, but sort of typical of some massive stars. Those we understand have masses in the range typically of about 5 to 15 times the mass of our sun. They might be bigger than that. Some of them are probably bigger. In fact, we know some of them are bigger because the gravitational wave experiments that have been done by the LIGO detector and Virgo, its counterpart in Italy, they've shown collisions with objects involving mergers of black holes, which are perhaps 20, 30 times the mass of the sun, so relatively big. But the smaller ones, 5 to 15 times the mass of the sun, revealing themselves actually by their X radiation. And so what you have, and this is a fairly common phenomenon throughout our galaxy. By that I mean we know of, I don't know, I suppose a few dozen of these things. I'm not an X-ray astronomer, so I might be exaggerating there, but certainly the very first one, Cygnus X1, works by this mechanism. If you have 2 stars, one of which and they get to the ends of their lives, one of which is massive enough that when it blows up as a supernova, its core collapses into a black hole. If you've got that phenomenon and another companion star in orbit around it, if that companion star is close enough, then you'll get material sucked off the companion star, which will go into the black hole of the accretion disk of the black hole. This is this spinning disk of material around the black hole, and that's where the X-rays come from, because there's so much energy in this spinning disk of material. The particles banging together, they actually create X-rays, and so you get a very strong X-ray source, plus the fact that there are these beams of material being spurted out from the poles of the black hole by the fact that it's highly magnetized. So that's the way that black holes, these stellar mass black holes, 5 to 15 times the mass of the sun, that's the way that they have mostly been discovered. But a group of scientists, if I remember rightly, they are mostly in the United States, yes, at the Ohio State University in the US. They've thought slightly outside the box about this and said, what if we're missing something here? What if there are some black holes in orbits around, or with other stars orbiting around them, which are not close enough to have this transfer of material from the companion star down to the black hole's accretion disk. Mm-hmm. So you wouldn't see any X-rays. You would not know that there was, that there was an X-ray source there. You wouldn't know that there was a black hole there. That's probably what I'm trying to say, because there's no X-rays being produced. And so what they've done is they've done what the planet hunters do. They've looked at the way stars which are visible in the sky, and they're relatively faint, but big telescopes can detect them, look at the way that they move with what's called the Doppler effect, the fact that as a star comes towards us or goes away from us, we can pick up its motion by means of the device we call a spectrograph, which breaks the light up into that rainbow of colors with the barcode of elements signatures imprinted on it. So you use one of those and you look for slight variations in the velocity of the star, which you can measure by means of the spectrograph. And if you do that over a long period of time, you can see the motion of the star, which is caused by something orbiting around it. And that's how we detect planets. It's called the Doppler Wobble method. We've talked about it many times before. But you can kind of invert that. You can look at the way a star's velocity is changing, and then you can infer from that it may well be in orbit itself around something highly massive, because you can do the geometrical, analysis of this sort of thing. And that's what these astronomers have done. They have detected something about 3 times the mass of the sun. That's the large star itself being tugged backwards and forwards by its companion object once every 83 days. But that companion object has a mass of probably 3.3 to maybe even as much as 6 times the mass of the sun. And the fact that it's invisible, because all you see is the star going around it, suggests that is a black hole. It's the fact that it's compact as well. So we've got here the first evidence that there is a class of objects that we haven't seen before, black holes, which are in that maybe 3 to 5 solar mass range, where you don't get X-ray emission from the material around the black hole, but you've got other evidence to suggest that it's there. So this is an interesting piece of research that may lead to a whole new field of study in black hole physics.
Yeah.
Just going to say there's a term for them. They're being called non-interacting black holes. That's to say black holes that don't interact with their companion stars.
Okay. Because we did talk, you mentioned at the beginning, there were 2 classes of black hole, the supermassive and the smaller variety. These are possibly smaller.
Smaller still.
We always thought there was, why wasn't there anything middle-sized? And we've started to discover, well, there are.
Yeah,
it seems, and now we're finding even smaller ones. So it's starting to look like they might come in all sizes. Yeah,
in all shapes and sizes. I have to say that the intermediate mass black holes, as they call things, with a mass of 100 or 1,000 suns, those are still very much in the minority. There are 1 or 2 that are candidates for those objects. But there's still a big gap between the black holes that we can detect by X-rays and the black holes we detect in the centers of galaxies. There's a big gap in there of missing intermediate mass black holes. That's a problem that I don't think has yet been solved. But this, in some ways, adds to the mystery, because it says, well, you can get even smaller ones as well that aren't interacting with their companion stars.
Yeah, it is fascinating, and so much more to learn. We'll crack it one day. It might take a long time. I wondered, though, while you were talking, if there have been discoveries in astronomy in the past where people have sat down and gone, now, wait a minute, we're looking at it from this perspective. What if it's something else? And they've started looking into it and gone, voila. Has that happened much?
Yeah.
Or does it happen like that all the time?
I mean, often, perhaps the classic example of that is that goes back to the 19th century when an astronomer called Leverrier believed that because of a peculiarity in the motion of Mercury around the Sun, he believed that there was a planet between the Sun and Mercury. And that was commonly accepted for 50 years, that there was a planet. It was called Vulcan. Nobody had ever seen it. People had tried to observe it. A couple of people thought they'd seen it, but it was never there. But it was just assumed by astronomers that it was a real object. And it was only when Einstein put together his general theory of relativity and found that the fact that gravity behaves a little bit differently when you're really close to the Sun than Newton predicted, that's then accounts for the observed anomalies in Mercury's orbit. And as soon as you put relativity into the thing, the need for Vulcan just disappears. It was a complete red herring. And who's to know? We might be following other red herrings in astronomy today, and people might look at Space Nuts podcasts in 20 years' time and fall about laughing because we were missing the point so much.
Yeah, probably Planet 9.
Yeah, there's all that as well. That's right.
Yes, all right. Very good. You're listening to the Space Nuts podcast. Andrew Dunkley here with Fred Watson.
0G, and I feel fine.
Space Nuts.
Thank you again to our patrons who have joined us on Patreon and putting their money where our podcast is. We really do appreciate your support, and if you would like to do the same, patreon.com/spacenuts is where you go, and choose your poison, basically. Patreon.com/spacenuts if you would like to contribute to the show. And another way you can contribute is by following us on YouTube, where, nearly 600 people have now started following the Space Nuts YouTube channel, which is fantastic. Actually, it just clicked over 601 as I spoke, Fred. So that is wonderful, wonderful, wonderful news. So thank you very much for your support of our podcast. Now, let's nail down some questions, shall we, Fred? This one comes from Robert Gola. Hi, Robert. I just recently discovered your podcast and have enjoyed listening to all episodes. You mustn't have listened to any yet. The ones you could find. They're all on YouTube, Robert, and just you can press play all and you don't have to worry. Then they'll just go. He says he's got a question. It's a very long one. Given that the planets in our solar system tend to rotate on their axes in the same sense as they revolve around the Sun, e.g. anti-clockwise when viewed from the North Pole, it seems that those objects that don't do that, like Uranus, are assumed to have had some dramatic thing happen in their past. Now, moving out in scale, our Sun revolves around the centre of the Milky Way. However, the planetary orbits of our solar system are tilted with respect to the plane of the Milky Way. One can see this because the path of the planets across the sky do not coincide with the band of the Milky Way. So, my question is, does this mean that something dramatic happened in the formation of our solar system to tilt it on its axis of rotation with respect to the plane of the Milky Way? Or is it simply wrong to assume that the sense of rotation of the Milky Way could be imparted on the developing solar system, since it is so far away from the centre of rotation and relatively small in size? I hope that was some way understandable. Actually, I know exactly what you're saying. It is a great question and well presented.
Indeed, that's right. And actually, Robert's got the answer in there as well.
Thank you, Robert. Next question.
It's quite right that the planets all rotate, I beg your pardon, revolve around the sun in one plane. Effectively, it's not quite, but it's much the same plane, and that plane is tilted over at a very steep angle. It's almost 90 degrees to the plane of our galaxy, the disk of the galaxy. But the reason why that isn't necessarily attributed to some dramatic event tipping over the solar system is because of there are two things. One is that the solar system is absolutely minuscule on the size of the galaxy. So if you think of the galaxy as this big swirling disk of stars, the solar system is almost invisible on that scale, and behaves like effectively a single point in terms of the gravitational field of the galaxy. Let me just give you an illustration of that, which I used to use a lot, and I'd kind of forgotten about until recently when I thought, this is a fantastic illustration. If you imagine a picture of our galaxy, a beautiful disk of stars and gas and dust, nice big portrait that you can put on your wall. Maybe the galaxy's a meter across or something like that. And now, instead of it being a meter across, think of that picture of our galaxy having the diameter of the Earth, 12,500 kilometers. So what is the separation of the Earth and the Sun on that scale? And the answer is 2 millimeters.
Oh.
And so that kind of gives you, the scale of a solar system compared with the scale of the galaxy. And so as far as the galaxy is concerned, the solar system is just a single point. The other thing is that there's the galaxy itself assumed its disk-like shape probably 12 or so billion years ago. When our sun and the solar system only formed 4.6 billion years ago by the collapse of a gas cloud that really itself was just the size of a particle compared with the size of the galaxy. So the dynamics of the two are really relatively independent. The galaxy, whilst it's true that the solar system does orbit around the center of our galaxy, it's not sort of gravitationally constrained by it in the sense that all solar systems are parallel to the rotation of the galaxy, so that you can regard them as being pretty independent in terms of the way their rotation has come about. But it's a great question. Thank you very much for that, Robert.
So it just is what it is, basically.
Yeah. So what Robert says is it that the solar system is so far from the centre of rotation and relatively small in size. That's exactly it.
Okay, very good. Thanks, Robert. We'll move on to our next question from Philip Eggert in Germany. Hello, Philip. I've got a cousin over in Germany at the moment. First of all, I love your podcast. I always listen in the car while driving back and forth from Germany to the Netherlands. Wow, that's a heck of a trip. Or maybe it's not. Just depends where you are, I suppose. I've got a question for you guys. When I heard a question from your last podcast about potential multiverses affecting each other through gravity, I thought about the possibility that instead of just bouncing against each other, like it is explained in many theories, they would merge. I know this is a very theoretical question with probably no definite answer, but I thought maybe you guys have your own thoughts on that. Hope you consider my question. I'm looking forward to your next episode, next podcast. Thank you, Philip. Well, we thought it was worth tackling right now.
Yeah, we did. That's right. So there isn't really, I don't think there is a straightforward answer to this, because the idea of multiverse, of more than one universe, it doesn't really fit the standard model of the universe. So the model we all accept is based on Einstein's theory of relativity, says that the universe exists in 3 dimensions of space and 1 of time, and that it basically has had a lifetime of about 13.8 billion years. And that there was nothing before it, because time itself started with the universe, with the Big Bang. So that's the kind of standard model. Now, beyond that, everything is hypothesis. And there are a lot of very serious cosmologists and astrophysicists who have looked in detail at this and have probably built theoretical frameworks. We spoke about one either last week or the week before, Roger Penrose, who's one of those astrophysicists who imagined that the universe, the multiverse, really itself is just a single entity that incorporates subunits which form from black holes, and of which our universe is just one. But another way of looking at it is to suggest that there is perhaps a higher dimensional space beyond the dimensions we can see. In what's it called? I forgot what it's called in Doctor Who. They've got a name for it, which I think might be the void, is it? I can't remember. There is a technical term for it as well, which is slightly different, and I've forgotten that too. So terrible. I should go and look these things up again before I start talking about them. No, it's called a bulk. That's
See
it.
how I saved you there?
Yeah. Did you? Oh, good. The bulk is the region outside normal space and time, and if that exists, for example, a fifth dimension, something of that sort, then it's not easy to see how, if you've got standard universes wandering around in this bulk, or the void as it's called in Doctor Who, how they would interact. Would they bounce off one another? Would they merge? We don't know. There's one theory, the only theory that I've really looked at in any detail, and it's a long time ago since I looked at it. This is the ekpyrotic theory, that suggests that you can imagine universes, just for the sake of argument, compressed into two dimensions. So they're in planes. So a universe is sitting in something like a sheet of paper. It's got a name. It's called a brane, and a brane is an abbreviation for a membrane. Those branes could perhaps collide, and the idea of those collisions would be, or the idea of the ekpyrotic theory is that collisions between two membranes or branes would actually generate a Big Bang phenomenon and give you the expanding universe. Now, there's a lot of theory involved in that, which I'm not really party to because I've not looked at the mathematics, and even if I did, I probably wouldn't understand most of them. But that suggests that that there is a kind of amalgamation. There's an interaction between multiverses that actually sparks, an event, a Big Bang event. So what it's saying is maybe not merging, but certainly doing a bit more than just bouncing off one another, perhaps, interacting with one another in a significant way. So I think Philip's thinking on the right lines, but I'm sorry I can't fill in too many of the details, but I think it's a really good, interesting idea.
Yes, indeed. And look, one that'll bounce around in people's brains forever, and we may never be able to solve that one. It's just, how do you observe another universe within this one, which is so vast, and unless they come up with some new concepts and theories.
I'm sure there'll be clever people who find a way. Maybe so.
We will see. Now, moving on, and thank you very much, Philip, for your question. Ralph Haney has a question from Petaluma in California. I hope I pronounced that correctly. Now, this is a really, really long question. He goes into some deep explanation about the fabric of time, and he's been struggling lately with the concept. I spent many evenings in our dark backyard observing our planet's rotation away from our star, the darkness of space filling my sky overhead, the distant light of other suns slowly revealing themselves. You've been writing a book or something. This is really nice.
Very poetic.
I take special note of the relationship of our spinning orb in relation to Polaris and the ecliptic with Jupiter, Saturn and our moon, trying to tangibly experience it in an objective off-planet perspective to grasp the big picture. Sometimes I succeed, and it's astounding. So he goes on to say, we're a small sphere spinning like crazy, orbiting a local star, being exposed repeatedly to direct energy, then blocked from it by our own mass. Day and night take on a new meaning with this greater perspective. But time is an enigma. we experience it as a linear phenomenon, always moving forward, never stopped and never reversing. As such, the starlight we receive in our night sky, even our own solar system's planets' reflected starlight, is always historical. Makes sense. But given that, how can we possibly plan a rendezvous with a distant object like Alpha Proximus or even Mars when the objects are no longer where we see them? How does NASA do this? Is it entirely by way of projections with supercomputers? And furthermore, if the nearest galaxy, Andromeda, is so far away, how do we know it still exists? I know the theory of relativity makes a strong case for the fabric of time, but my feeble brain has a hard time pulling it all together. Truly, time is enigmatic. Love the show, Ralph Haney. That's a brilliant question, just so well put together.
Yeah, it is. And it is, it's very a very articulate question as well, indeed, if I may say so.
But look, basically what he's saying is, with everything moving all the time and being so far away from us, how on earth do we know where things are, or even if they still are there?
Yeah.
And sometimes they're not.
That's right. But often we know where they are, even if they're not where we thought they were, if I can put it that way. Let's just go. There are really two questions here. One is about rendezvous with objects in the solar system, and that's really pretty straightforward, because you, as soon as you know the orbital parameters of a planet, for example, then you can build in the fact that the light travel time from that planet is, however many seconds multiplied by the speed of light. Sorry, I've got that the other way around. It's the distance divided by the speed of light. That's so it works. It works really well, and my experience of this goes back to when I used to work, and this is many years ago, when I used to work on the orbits of asteroids. Was what I did for my master's degree. And in all the equations where you're looking at the positions of asteroids, you always have, or when you're relating them to observations from the Earth, you always put in a term that involves the speed of light. There's a delay factor caused by the fact that the light travel time is not zero. There's always a travel time, and that actually works very well. And it's how we steer things around the solar system. Likewise, with anything in our galaxy, if we had spacecraft that could travel at close to the speed of light, and we were trying to rendezvous with the nearby stars around the sun, like I think actually what Ralph means is Proxima Centauri, which is the nearest star to the solar system, then we could do the same thing, because the motions of stars around the sun are pretty well known, they're pretty well established, and once you know that, then you can compensate for their motion when you do a rendezvous. But the bigger question is about whether, how do we know whether distant objects still exist? Andromeda certainly will. Andromeda is only 2 million light years away, exactly as Ralph says. That's very much on our doorstep in terms of the world of space, or if I can put it that way. It will exist, and we kind of could work out its position if we were ever going to try and travel there. I don't think that's really on the cards at the moment. For more distant objects, the bottom line is, when you're looking at the universe as a whole, the only way we have of getting any information about the universe is by virtue of things that travel at the speed of light, either radio waves or X-rays or whatever they are. They're all coming at the speed of light. And so in a sense, the universe itself only exists in this relative dimension. We can imagine, okay, let's imagine looking at the universe as a whole from the outside, and what's happening are things coming into or going out of existence. That might be the case, but none of that has any meaning to an astrophysicist, because everything comes to us by virtue of things being transmitted at the speed of light, or sometimes a little bit less in the case of subatomic particles. So we always envisage or think of the universe in terms of what we can actually see. And it may well be true that some distant objects aren't there anymore. In fact, there's a classic example of this. Quasars in the modern universe are extinct. We don't see them in the modern day universe. But as we look back in time, we see these objects. They're actually delinquent galaxies. They're the nuclei of galaxies that have got a hyperactive black hole in the middle, doing all sorts of things to their surroundings. But they don't seem to exist in today's universe. So if you think of the universe as a whole, then there aren't any quasars in it, but we see them ten a penny because we're always looking back in time. I don't know whether that helps, but that is the way the world of astrophysics looks at things.
There you are, Ralph. Easy. Thanks for your question. Really appreciate it, and we appreciate all your questions and all the activity on Facebook and just some of the comments. We did actually get a nice comment the other day, Fred. I meant to mention it this episode, and I'll see if I can find it very quickly. From calls himself Jabba Steady. Loving your work, guys. Great to listen while lazing by the pool. So people can listen anywhere, anytime. It's the beauty of podcasts. Now, before I let you go, Fred, a reminder to everybody that there is a Space Nuts shop. You can find it on our official website, bitesz.com/spacenuts. That's BITESZ. Apparently the proper way of spelling it was taken. bitesz.com/spacenuts. You can listen to all our episodes there. You can sort of slide down and there's Cosmic Chronicles and a couple of other books by Fred. Why is Uranus upside down? There must have been something he ate. And Fred Watson's Star Craving Mad and a few other very questionable publications. But there's T-shirts there as well with the Space Nuts logo. Lots of people asking how to get hold of T-shirts, so that's where you go. bitesz.com/spacenuts. Fred, thank you as always. Great fun again.
Thanks very much, Andrew. Great fun to talk to you too. And, maybe we should do it again sometime.
I'm thinking we might do it in a millennia or two. Millennium or two.
A millennium. A week could be better.
Yeah, okay, we'll do that.
Right, let's do that.
Thanks, Fred. See you soon.
See you later. Bye for now.
And thanks for listening. Thanks for being a part of the Space Nuts crew. It's always good to have you involved, and we look forward to joining you again next time on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor. This has been another quality podcast production from Bitesz.com.